So we're going to start our foray into counting theory with talk about permutations. That word is just asking you to count the number of ways that you can arrange a certain number of objects. This field is particularly interesting for programming or for like code breaking or code making, encryption, that sort of thing. Because if you take a sequence of letters and numbers, there are only so many combinations that you can assemble. So, for example, your locker combination, there are 60 positions on that lock, and you only choose 3 numbers. So there aren't an infinite number of locker combinations. If you had the time, you could sit down and try each and every combination, and eventually you would get into that locker. Now that's fine for a locker because someone will get suspicious if they notice you standing there for 17 or 18 hours trying each combination one after another. But if you were a computer and you could rifle through those combinations with processor level speed, then a locker, like a combination lock, isn't enough to stop you from breaking in. So if you've ever noticed on a router, if you try to get the Wi-Fi password for someone, usually the string of characters is about this long, and it's in hexadecimal, which means it's not numbers 0 through 9, it's the numbers 0 through 9 plus A, B, C, D, E, and F. So it's a 16-digit encryption 16 ordinal, I guess, encryption with a large string of them together, just so you can make a larger pool of passwords to draw from, so that you don't just have a computer hopping on there and then dedicating its processor to hacking your Wi-Fi. Anyway, I'm a little off topic. So the idea of permutations is just trying to sort things. And I'm going to stick to problems where I sort letters, because they're fairly easy to conceive and they're fairly easy to make the lists of. So let's just try one and see what happens. So I'm going to take a nice short little word like hand. So the word hand has 4 letters in it, an H, an A, an N, and a D. And so a classic permutation question would be, how many different words can you make out of the letters in the word hand? Now, word doesn't mean it has to be pronounceable. It just means a sequence of those 4 letters and all of the possible shufflings. So I'm just going to write that out there. How many words can you make with these letters? Well, the clumsy way is to make a list. So we're going to do that first. What would be better is if we could find a way to calculate this based on the features of that word, so that we wouldn't have to make that list. If you imagine something like, well, locker combinations, that's a good example. How many of those are there? Lots. So if you had to actually write them all out and then count them, that would be exhausting. That would take just as much time as to actually break into someone's locker by brute force. So there must be a smarter way to do this. So let's find out what it is. So I'm going to start with this list. I could start my word with an H, and then follow it with an A, and then an N, and then a D. Well, that's the obvious one. That's what we started with. Now, to keep this organized so I don't lose any combinations, or permutations, sorry, I'm going to leave the H where it is. I'm going to leave the A where it is. I'm going to switch the D and the N. Hadden. Well, that's not a word, but it counts here as a permutation of the letters. So these are all of the words that start with an H followed by an A. So I'm going to come up with all of the words that start with an H followed by an N. Well, that could be H-N-A-D, or it could be H-N-D-A. All right? I need the letters or the words that start with an H followed by a D. So this would be H-D-N-A or H-D-A-N. So that should be all of the words that start with an H. So I'm going to have to go through and I'm going to have to do this again for all of the words that start with an A. And then I'm going to have to go through and make this list for all the words that start with an N. And then for all the words that start with a D. So do you notice that I'm going to have to make this list again? These were the ones that start with H. There's going to be a list that starts with a list that starts with D, and a list that starts with N that I haven't drawn yet, and I don't want to do it because it's going to take a long time. But if you imagine this one here, the ones that start with A, well, the A would be here, and the H would be there instead. So if I went through and did these combinations, it would be A-H-N-D, A-H-D-N, A-N-H-D, A-N-D-H. I'm just replacing the H and the A because I've switched who gets to be priority in this list. There's going to be the same number in this list as there were in that one. So there's 1, 2, 3, 4, 5, 6. So there's 6 here, 6 that start with H. So there's going to be 6 that start with A, and then 6 that start with D, and 6 that start with N. So I'm going to have 4 lists, 1, 2, 3, 4, all of which have 6 different permutations in them for a total of 24. Now you see I already used the shortcut. I already went through this, started making the list, saw the pattern, and then abandoned the project because it was tiresome, and went straight to the calculation. There's nothing wrong with that. The question was not make a list of all these words. It was how many can you do? So if you see a pattern you can leap straight to it, then by all means. So I'm going to take this. This is the answer we're after. I want 24 different things. And I'm going to try and do this without making that list in the first place. So let's clean this off. And the trick to this is setting up a model for your word, and then just thinking about how many things would fit into that model. So hand has 4 letters, and we're making 4-letter words because we're using all of them. So here's a slot for my first letter. Here's a slot for my second one. Here's a slot for my third one. And here's a slot for my fourth one. So when I go to make this list, the first letter here is either an H, or it's an A, or it's an N, or it's a D. There are 4 different ways that I could choose my first letter. Now once I do that, so pick one in your head, it doesn't matter. Whatever one you just picked isn't available to be the second letter. So in this example here, once I select H as my first one, I can't have H as my second letter. It's already been picked. Which means that I have 1 fewer option here. There's only 3 left to choose from. So if you pick the H as your first letter, then only the A, the N, and the D are left to be the second one in your word. Okay, well if we keep doing that, when I get to this letter, There were 4 for me to pick from. I already used one, and I already used another. That leaves 2 left. There's only 2 here. And by the time I get to that last letter, I've picked the first, I've picked the second, I've picked the third, and whatever poor sad sucker is left at the end is the only one that can be last. So this maybe looks a bit like a tree diagram to you. Notice that you could have picked H or A or N or D. And if you picked A, then you could have picked H or N or D. Right, this sort of thing, which is also tiresome. If you picked an A, then a D, then you could have picked an N or an H. And if you picked A, D, N, the only letter left is H, and the only letter here is N. You could draw it that way too. Notice that for each of these 4 branches, there are 3 branches. And for each of these 3 branches, there are 2 branches. And for each of these 2 branches, there's only 1. So in order to get out to here, you had to pick your first letter, and your second, and your third, and your fourth. Now in the probability unit, anytime you said the word and, it was implying that you needed to multiply things together. So if I have these numbers, there's 4 ways to pick my first letter, 3 ways to pick the second one, 2 ways to pick the third, and 1 to pick the last, then I should take my choices for the first one, multiplied by my choices for the second, multiplied by my choices for the third, multiplied by my choices for the one, or for the last. 4 times 3 is 12. 12 times 2 is 24. 24 times 1 is 24, which is the answer we arrived at last time. So that's encouraging. And in fact, this is how you end up doing permutations. You take the number of objects available for your first slot, multiply it by the number of objects available for your second, which is 1 less than before, then 1 less, then 1 less, until you run out. So this operation, because it's so common, it gets its own button on your calculator and its own function. So we would abbreviate this as a 4 with an exclamation point at the end. And you would call that 4 factorial. It's kind of like you're taking number 4 and yelling about it because you tacked an exclamation point on the end. It's basically telling you to start with this number and then multiply it by every number that comes after until you get to 1. So this factorial function is the fastest growing function that's available. It's very aggressive, it gets very big very fast. It's even bigger than the exponential function. If you're taking advanced functions and you know what I'm talking about, then that should be terrifying. Because exponentials take off, right? And boop, up they go. This one is much more aggressive than that. But we're going to be using it quite a bit in permutations. So if I can give you another sort of simple example of this. So we're going to try making all the combinations from the letters in the word pencil. If you count them, 1, 2, 3, 4, 5, 6. There are 6 letters in the word pencil. So if you were to set up your diagram, you're going to have to pick the first letter, then the second, then the third, then the fourth, then the fifth, then the sixth. When you go to choose your first letter, you can pick any of them. So there are 6 available for you to choose. When you go to the second letter, you can use anything except the one you just used. So that leaves 5 choices. And then here you can use anything except what you've already used. That leaves only 4, then only 3, then only 2, then only 1. So you could get this answer by doing 6 times 5 times 4 times 3 times 2 times 1. Or you can hunt on your calculator and find that exclamation point button and use the factorial function in order to answer this. So if I were to do that, 6 factorial, if I type that into my calculator, if I can find it on here, 6 exclamation point is 720. So there are 720 ways you could arrange the letters in the word pencil. Lovely. If we were doing much larger words, right, something like spaghetti or onomatopoeia, there's a lot of letters there. And if you had a 23-letter word and you were trying to sort them out, 23 times 22 times 21 times 20, that's going to take forever. That's what this button is for, so that you can just do 23 factorial. And then the calculator will spit out this monster number and save you the energy of having to multiply this by this by this by this an enormous number of times. So sorting letters in the word pencil is maybe a bit abstract. I mean, who cares? But if you were running a race, right, the 100-meter dash, if you look at a track, there are 6 lanes in that track. So that's 1 lane per letter here, which means 1 lane per athlete. And when you are watching a race, the only thing you care about at the end is what order did they cross the finish line. So if these letters, instead of spelling pencil, were the first letter of their first names, so, you know, Peter, Edgar, Nancy, Chris, Imogene, and Larissa, this particular word is describing where Peter won the race. And I forgot the names, but whoever these 2 people were, first, second, third, they got ribbons, and then these 3 people were noted down on the scorecard but didn't win anything. In a different combination, maybe L wins, P comes in second, and C comes in third. But if you think about this, and this is the part that changes your whole perspective of the universe, if you put 6 people in a race, in a 100-meter dash, there are only 720 ways that race can play out. Some of them are more likely than others, but there are a finite number of ways that event can take place. And you're maybe used to the comfortable thought that, like, anything can happen. Well, that's not really true. The entire universe is based on atoms and molecules and little building blocks, and there are finite numbers of them, and they can only come in certain orders. So the universe has this feature built into it that anytime you start combining little pieces, there is a finite number of ways in which you can do it. And if you can start counting those things, then you can start making probability decisions based on them, and you can, to some degree, model the future. I mean, this is what weather patterns do. This is what people who invest in stock markets do. They take these numbers and the possible combinations and all the possible outcomes, assign probabilities to them, and then make a choice about what you think might happen, or how much you're willing to risk based on the chance that it will. Again, I've gotten off topic. But back to sorting words. I'm going to change this word just a little bit. If I try to do all the arrangements of this particular word, fluffy, this has 1, 2, 3, 4, 5, 6 letters in it, just like pencil. So you would think that there would be 720 different arrangements of that. To illustrate why it's not, I'm going to change this F to blue marker and this F to yellow marker. One of these combinations is F in pink, F in blue, F in yellow, L, U, Y. Okay. Another one of these arrangements is F in blue, F in pink, F in yellow, L, U, Y. Now that looks different because I colored the F's different colors. But when you read, well, when you read English anyway, the color of the letter does not change your pronunciation, and it does not change the meaning of the word. So like the word cat written in pink doesn't mean something different than the word cat written in blue. It would certainly make language more interesting, and I think English is already complicated enough. This word would be pronounced floy, so is this one. So that's not a different word. Even though it's a different arrangement of the letters, it did not make a different word. So I'll have too many combinations. 720 is too many because it includes these arrangements. Well, how many arrangements of those F's are there? Well, there's 3 of them. And if I were to take my F's and figure out my 3 different orders I could put them in, well, that's just 3 F's factorial. So there are 6 different ways that those F's could appear inside of my word. So if I have repeated letters, I need to divide out this many combinations. I have to divide out the shufflings of my repeated letters. So in the word fluffy, there should be 6 factorial shufflings because there are 6 letters. But then I have to eliminate 3 factorial worth of repeated letters. So if I put that in the calculator, 6 factorial is 720. And 3 factorial would be 3 times 2 times 1, which is 6, for a total of 120 different ways. So let's try a more complicated one. SAS. There are 4 letters in this word. So that should make 4 factorial arrangements of those letters. But 3 of them are indistinguishable. I can't tell these S's apart. So I need to divide out the shufflings of those indistinguishable S's. Now 4 factorial would be 4 times 3 is 12 times 2 is 24. And 3 factorial is 3 times 2 times 1, which is 6. And so I would end up with 24 divided by 6, which is just 4 different ways. All right. We'll prove it. Okay. You could have as, or you could have sas, or you could have sas, or you could have sa. And that's it. That A is either here or here or here or here. There's nowhere else you can put it. So despite the fact that this has 24 different shufflings of the letters, because 3 of those letters are indistinguishable, there end up being only 4 distinct permutations of those letters. So now that we've done the medium one and an easy one, easy in that I can write the list without taking up 6 hours. Let's try one that's a little more complicated. Goodness, everybody's favorite state to spell, Mississippi. Okay, so if I were trying to come up with all of the unique permutations of the letters in the word Mississippi, I would have to figure out how many letters there are in the first place. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So without considering anything, I'm going to start with those 11 factorial shufflings. That 11 letters have this many arrangements. So I'm just going to figure that out. 11 factorial see, 11 exclamation point is 39,916,800. You see how this function gets really big really fast. But as we discovered in the word sass and in the word fluffy, this is too many, because some of those combinations are just resortings of the s's, right? These two s's switch places. So I need to divide this down in order to eliminate some of those repeated outcomes. So I'm going to get myself a dividing line here to start eliminating combinations. So first off, there are 1, 2, 3, 4 i's. So I need to eliminate the arrangements of those i's. There are 1, 2, 3, 4 s's. So I need to eliminate the arrangements of those s's. And there are 2 p's. So I need to eliminate the arrangements of those 2 p's. So basically I'm taking a shuffling of all the letters and then dividing out all of the shufflings of anything that is indistinguishable. So 4 factorial, 4 times 3 times 2 times 1, we've done already, is 24. 4 factorial, again. 2 factorial is just 2 times 1, so that's 2. And then you are going to proceed with caution using your calculator. You might be tempted to type in 39,916,800 divided by 24 times 2. But if you do that, what your calculator will hear is this divided by this, and instead of dividing by these two numbers, it will multiply them. So that's, you got to watch that. I would highly recommend you do all of this multiplication in the denominator first, so that that doesn't happen to you. So 39,916,800 divided by 24 times 24 is 576 times 2 is 1,152. Now that I have that all sorted, I'm going to do my big number. 11 factorial divided by 1152 is 34,650. Now that's really cut down. You'll notice 39, almost 40 million down to only 34,000. That's quite a change. Right, this number, when you get to these combinations, these numbers are maybe hard to wrap your brain around. But in this country right now, there are somewhere between 30 and 40 million people. So that's the number of Canadians. This is the number of people who live in a mid-sized city. So something like, well, Owen Sound isn't quite that big, but 1.5 Owen Sounds certainly would. If you were to take the population of Hanover, Walkerton, Chesley, and Owen Sound and add them together, you might get something like this. That's quite a difference from the entire population of the country. But that sort of circles back to the idea of locker combinations and passcodes. If you needed to assign every Canadian citizen a security number, a social insurance number, for example, you need to have like 11 factorial combinations of those letters in order to get enough of them. If you only gave them 6, right? If your SIN numbers, this is silly, but if your SIN numbers were the shufflings of the letters in the word Canada, for example, there wouldn't be enough for you to assign one unique passcode to every person. So just let that sort of boil around your brain. So we've done a question where there's some repeats. We're going to do a question where we're not going to use all of the letters. So let me clean this up, make some space. So how many 4-letter words can you make with the letters in the word leading? So there are 1, 2, 3, 4, 5, 6, 7 letters available to us. So we're going to end up leaving some behind. In fact, that means we have to leave 3 behind, right? If you use 4, use 4 of 7 means leave 3 behind. Okay. So I'm going to build the little box model for these words. So there are 1, 2, 3, 4 letters in my 4-letter words. And I have 7 distinct letters to choose from in my first box. It could be the L, the E, the A, the D, the I, the N, or the G. So that's 7. Now, whatever I pick for the first one, I can't use it, so I'm left with only 6. And then I can't use these 2 for here, so I'm left with only 5. And then I'm left with only 4. Now, I didn't make it all the way to 1 because I stopped using letters before I ran out of letters. But in order to build these words, I had to pick something for the first, then and the second, and the third, and the fourth. So I'm still multiplying. 6 times 5 times 4, which ends up giving me 7 times 6 times 5 times 4 is 840. So I can do that manually, it's no problem. If I'd had a longer word, like disingenuity, and I had to make 8-letter words out of that, then I would have had to do something awful like 17 times 16 times 15 times 14. I don't want to do that. So just to shortcut this, 7 times 6 times 5 times 4, that looks a lot like 7 factorial. Except 7 factorial would have a times 3 times 2 times 1 attached to it. So in order to get this number here, I would have to divide by 3, by 2, by 1. So that this would divide out this would divide out that, and that would divide out that, and leave only 7 times 6 times 5 times 4. Well, you notice this number here, 3 times 2 times 1, that's 3 factorial. And if I take a look at some of the information I wrote up there, do you notice in this line it says that using 4 of 7 means that you leave 3 behind? So if you're not using all of the letters, it looks like you shuffle all of the letters, but then you divide out the shufflings of the ones you don't use. So if I were to sort of give you a specific example here, one of the combinations in leading is L, E, A, D. Those are my 4 that I'm taking. And then my shufflings of the back, I could have gone lead, I-N-G, or I could have done lead, I-G-N, or I could have done lead, N-I-G, or I could have done lead, N-G-I, or I could have done lead, G-N-I, or I could have done lead, G-I-N. Well, I don't care because I'm not actually using these letters. But those are all of the shufflings of these 7 letters that start with L-E-A-D. So that would be 7 factorial arrangements, and I have to divide out these 6 because I'm not using them. And that's what's happened over here is I took the 7 letters and shuffled them, 1, 2, 3, 4, 5, 6, 7, shuffled them all up, and then collapsed these 1, 2, 3, 4, 5, 6, these 3 factorial arrangements of the letters I don't care about. So if we were to try a slightly bigger one, I don't know what a bogmaster is, but it's hard to find words that are long that don't have repeated letters, and you'll see why I'm avoiding that shortly. So if I take the letters in the word bogmaster and I'm trying to make 5-letter words out of them, using 5 out of 1, 2, 3, 4, 5, 6, 7, 8, 9. Using 5 out of 9 means leaving 4 behind. So I'll give you a minute to think in your head what this fraction should look like. Okay, maybe not a minute. I have 9 letters, and it's a shuffling problem, so I'm going to need to shuffle all 9 of those letters. So let's get that out of the way. Then if I look at what's left here, I'm leaving 4 behind. So there's a shuffling of 4 letters when I'm finished here that I don't care about. So I'm going to divide them out. So 9 factorial is 362,880. And 4 factorial is 24. So 362,880 divided by 24 is 15,120. So there should be 15,120 ways of selecting and rearranging only 5 of those letters. All right, so we have done permutations where some of the objects, some of the letters or things that you're shuffling can't be, that they're indistinguishable, right? Like 2 S's, you can't tell them apart. We have done permutation questions where you don't use all of the objects. You only use 5 of 9. The third type of question you're going to encounter is one that has a condition on it. So how many 5-letter words can you make with the letters in the word bogmaster if they must start with M-A? So as soon as you get a condition thrown in there, you have to go back to the basic idea of how you built these words and start with the structure of them and then maybe do some counting after that. So if I were to make these 5-letter words that start with M-A, well, they must be M-A. And since it's a 5-letter word, I need to fill in 3 more spots. So if I think about that, once I take the M and the A out of here, I have 1, 2, 3, 4, 5, 6, 7 choices left. So I'm going to end up shuffling those 7 letters. But out of the 7, I'm only using 3, which means I'm leaving 4 of those letters behind. So 7 factorial, I think we had this before, but I have forgotten the number. 7 factorial is 5,040. 4 factorial is 24. For a total by 24 of only 210. Well, that's considerably less than the 15,000 or so we had before. So this condition, if you see one, try and model the word that you're trying to shuffle or model the situation, right? So if it was Max and Andrew always have to get into the school first, so you put Max and Andrew in line, and then whoever these other 3 dummies that get in line behind them, you are free to shuffle, but Max and Andrew have to go first. So I'll leave you to think about that. The last thing we have to talk about here is when you try to blend these 2 ideas. You notice that in this one, I was able to attach a condition and leave some behind, and it didn't screw it up. I should be able to attach a condition to repeated objects and not screw it up. But what we have to watch out for is if you have repeated objects and you're not using all of them. So I will try and Imagineer one out of here for you. So we're going to circle back to this fluffy question, but instead of shuffling all of the letters, I'm going to only have 2-letter words. So the things that we talked about before, and keep in mind, what I'm about to do is wrong. And I'm trying to do it, I'm doing a bad question for you so that you can see how things can go wrong and how to know that your answer doesn't make any sense. So just keep that in mind. The first thing we did was that there were 3 F's. So triple F meant we were going to divide by 3 factorial. That's the shuffling of those F's. Now this condition here, that we're only making 2-letter words, well, using 2 of 1, 2, 3, 4, 5, 6 means you leave 4 behind. So we did examples like that. It just meant you had to divide by 4 factorial to throw away the ones that you were leaving behind. Well, sure, I mean, that's what we did in the other examples, but watch what happens if you try to do both of those things. So there are only 6 letters, so I'm going to shuffle them all, and then, presumably, divide out the shufflings of the F's, and then divide out the arrangements of the letters I'm not using. Well, 6 factorial is 720. 3 factorial, 3 times 2 is 6. And 4 factorial is 4 times 3 times 2 times 1 is 24. Which gives me 720 divided by 6 times 24 is 144. Ooh. Sorry, I've made a number error and now I have to come back and try and pick up the thread where I left off after re-recording this video. So where were we? 720 arrangements of 6 letters. Get rid of the 3 triple F's and the 4 letters we're leaving behind. Leaves you with 720 divided by 144 is 5. So if I apply this technique of getting rid of the triple F's and this technique of getting rid of the shufflings of the 4 letters we leave behind, I should end up with 5 possible 2-letter words. But if I were to actually sit and make the lists of 2-letter words I can make from these letters, well, I could use 2 F's, or I could use 1 F with the L, or 1 F with the U, or 1 F with the Y. Or I could switch the order, the LF, UF, YF. Well, I'm already over 5 and I'm not done yet. Or I could try them with no F's, which would be the L with the U with the L with the Y with the L, or U with the Y, and Y with the U. So it looks like I have, what is that, 13 different words, and my calculation came up with 5. And the problem is that you can't combine these techniques. It ends up undercounting too much. One of the good ways of spotting that you've done this is if this number ends up as a decimal, you notice that in none of the examples we've done so far, even though we're dividing crazy numbers by other crazy numbers, it never came out as a decimal. It was always 8 or 12 or whatever. No 5.6s or anything like that. if you get a decimal in a counting theory problem, something has gone wrong, because you can't have 8.4 arrangements of the letters in the word fluffy, right? It's either 8 or it's 9, and you should never have to do any rounding. So this example here, where the triple F's and the technique of getting rid of them, and the leaving 4 letters behind and the technique to deal with that, they've conflicted with each other and ended up reducing this problem too much. If that happens to you, that you end up with objects that are indistinguishable and you are leaving some behind, then you have to use a technique called cases. And that's what I've done here for you. Case number 1 is if I take 2 F's. Case number 2 is if there's only 1 F. Case number 3 is if there are no F's. And the final case that I've left out would be the case where there are 3 F's, because I have 3 available to me, but I can't make a 2-letter word using 3 F's. So there's going to be a video later about how to build these cases more specifically. So when you go to the practice problems, what I want you to do is I want you to read through them, and I want you to ask yourself 2 questions. First off, are there any indistinguishable objects, like triple F's or triple M's, or cans of Coke? You can't tell one from the other. Anything where you look at the 2 or 3 or 4 objects and you can't tell them apart. Are there any of those? And then ask yourself if you're leaving any behind, or if you're using them all. And if there are indistinguishable objects and you are leaving some behind, it's a cases question, and all I want you to do is write indistinguishable objects, leave some behind. And then you're going to write the word cases in a great big circle. And then you're going to walk quietly away from the problem and leave it for later. Part of the exercise here is being able to read through a complicated set of permutation problems and recognize, is it the type of problem where I'm eliminating indistinguishable objects? Is it the type of problem where I'm leaving some behind? Or is it a hybrid question where I have to do something more complicated? So they're in there for that reason. Like, they're little landmines for you to step on if you don't spot which ones need cases. So I want you to hunt, and if you find one that says cases, you just write this on that question, and then we'll cycle back to it later.